Boa noite. Welcome, everyone. I am Elisa Junqueira de Andrade. I am the coordinator of the Strategic Research Area of Energy at the Norwegian University of Science and Technology. And today we have a panel on hard-to-abate industries, cutting emissions and improving efficiency at the same time. We'll talk about sectors aluminum, cement, steel, fertilizers that are critical to global development, but also major contributors to emissions. And we will explore how industry and research can work together to deliver deep decarbonization while maintaining competitiveness and social equity. I will guide our discussion in the light of the Belém Declaration on Global Green Industrialization that was launched last Friday here at COP30, which calls for accelerating industrial decarbonization in a way that is just, inclusive, and aligned with the Paris Agreement and NDCs. Our goal is to connect these principles to practical action. To set the tone, I would like to invite on stage Niels Roque. He's the Executive VP of Sustainability at SINTEF. Welcome, Niels.
Maybe we could get the background. Oh, there it is, you know. It's all automatic. Yes, so thank you very much. My name is Niels Roque. I'm EVP for Sustainability in SINTEF. SINTEF being a research and technology organization counting about 2,200 people in Norway. And welcome to this event being supported by a report we just released here at the COP, which talks about what are the important climate technologies we can use, the technological solutions towards this, and guide the negotiators and decision makers, hopefully, in the discussions here to guide us towards the Paris Agreement. Even if we know that at the present state of the NDCs, we're not going in that direction, but at least what could we do more? And I think that is also guiding a lot of discussions here. What happens if the NDCs does not match the Paris Agreement? The hard-to-abate industries such as cement, steel, aluminium and chemicals are the backbone of modern economies, yet they account for a significant share of the global greenhouse gas emissions. Decarbonizing these sectors is complex because the processes are energy intensive and deeply integrated into global supply chains. The challenge is not only to cut emissions, but to do so while maintaining competitiveness and improving operational efficiency. This requires a dual focus, deploying breakthrough technologies and optimizing resources to deliver low carbon solutions without compromising productivity. Industry depends a bit on how you define this, but typically accounts for about 25% of the global CO2 emissions, with said sectors, cement, steel and chemicals being the largest contributors. Tackling these hard-to-abate sectors is essential for meeting the Paris Agreement's targets, or shall we now say we used to talk about the 1.5 target. We are probably more now towards the 2-degree target. And progress is slower than anticipated. Some sectors can be electrified, some not. A diversified set of actions are needed. Be it CCS, hydrogen, change of materials and processes, to mention some. Today we have 3 sectors represented here: aluminium, fertilizer and cement as the industrial representatives. Aluminium and the whole value chain, from bauxite to alumina and aluminium using electricity through carbon anodes emit CO2. I recall myself trying to measure CO2 from one of the flue gas ducts in Norway in the aluminium smelter plant with a variety of other gases, and having problem to measure the CO2 at a meaningful concentration and to correct to a standard concentration without large errors. So there are low concentrations These are better from the pre-baked than from the older Söderberg type oven, but still a challenge for conventional CCS. Closing the cells and developing new processes using, for instance, chlorine or CO2 electrolysis, I've also seen being suggested, can change the pattern completely. Fertilizer production uses hydrogen to make ammonia, mostly sourced from natural gas reforming without any kind of CCS, emitting about 10 to 12 kilo per kilo hydrogen produced. Switching to electrolysis with renewables or large-scale blue hydrogen, which includes CCS, can reduce emissions, which currently account for about 1.2 to 1.3 of global emissions from the production alone. And cement, yes, about 7% of the global emissions. 2/3 coming from the material itself in the calcination process, and the remainder coming from the heating process, firing the rotating kilns to make clinker. Options include fuel switching. In principle, you could use electricity. CCS, obviously, as we've seen that deployed also in Europe. Alternative materials, clays, other additions to the mix forming the clinkers. What is common for all these industries here today is a very competitive market. Thus, we need to think larger and really big picture. At the project level, low-carbon cement is not a real price driver. Cement, even doubling the cost of making that from low-carbon cement, it may only add up to 1 to 2% of a large construction. We actually made a paper about this in 2023 about the Bridge Lake Pond Chartrain Causeway in USA, figuring out that there is 1 to 2% price increase by using low-carbon cement. And the same applies to cars, using low-carbon materials, single-digit additions, both for green steel and low-carbon aluminium. This shows the power of public procurement and customer purchasing power. In my view, we have to make the green premium the standard solution. In such a system, the unsustainable solutions should be more costly because they cost us more ultimately. As the title for this session implies, energy efficiency is also part of this effort to reduce emissions. Using less resources for the same outcome is a very powerful tool for energy and resource conservation. Doing both decarbonization and make more efficient is the challenge at hand. Now, I'm not to keep you longer on my speech here and keep you from the specifics, as we have the experts here today, which can give you more detail on the solutions they are pursuing in real plants, and also what are the prospects. So with that, I invite the other speakers to the podium and leave it to Eliza to moderate, and thank you.
Thank you, Niels. That sure gives us a strong foundation to start our discussions. And now we will hear from our industry leaders who are in the front line of these. Each of the sectors we'll discuss today have their own unique challenges, but also a lot of opportunities for innovation and collaboration. And we will start with Björn Mauritzen, Head of Sustainability at Hydro Aluminium. If we can get the slides back, please.
Okay, thanks a lot for that introduction. Hydro, we are an aluminium and renewable company. We operate mostly all over the world in North America, Latin America, Asia, Middle East, Nordics, Europe. Everything starts here in the state of Pará. We have a mine, we have the world's largest aluminum refinery, and we also have a smelter here. We also have, this is also where we will reduce most of our emissions in this decade. I'll come back to that later. just to give a little bit of we are a fully integrated company. That means that we have full overview and control over all the sustainability data, especially when they come to carbon, throughout the value chain. And this is very good when we are in a situation where customers ask what is the actual footprint of the metal that we are buying from you, because our scope 1 and scope 2 are our customers' scope 3. And luckily we're seeing a lot more interest on what the carbon footprint is, and we are working very hard to develop markets for low carbon solutions. But to do that, we need to reduce our emissions. So here, one way of looking at our emissions when you divide it by scope 1, scope 2 and scope 3. So scope 1 is basically coming from the electrolysis on the smelter, but also coming from energy consumptions at alumina refining. Scope 2 is relatively low for us as an aluminium company, because almost 80% of all our energy consumption is already based on renewable. And then scope 3 is basically all the cold metal that we are buying. We produce 2 million tons, but we sell 4 million tons. So we buy a lot of metal. Our scope 3 numbers, because we are a fully integrated materials company, vary very much from year to year. So for instance, like now, there is an economic downturn. We don't sell that much aluminium as we like to sell. We reduce external purchases of cold metal. And then of course we use the relative share of our own metal, where we have already accounted for the scope 1 and scope 2, will increase. So from one year to the other, we have improved by 20% just due to the economic downturn. So a lot of people are concerned, want to know the scope 3 numbers, but for an integrated materials company that actually produce something, they are very volatile. Then this is also an overview over the emissions on the 4 different business areas. So bauxite and alumina here in Brazil, they have an important share of our emissions, but the largest is coming from the aluminium metal, the smelters. And there you have direct emissions, and then we also have some scope 2. This is coming from 2 smelters, one in Qatar, which is running on gas-fired power, and we also have a small ownership share in a smelter in Australia, which is basically buying power just off the grid, and the Australian fuel mix is quite large. There's a large carbon content, coal and gas in the Australian fuel mix. And then extrusions, 22,000 people working there. 2/3 of all Hydro employers are working in this part of the business, but they have by far the lowest footprint, because it's not energy intensive at all compared to the other. And then energy, they're basically producing renewable energy, so the footprint is low. Also here in geography, Europe, emissions coming from the direct emissions on the smelters, very little scope 2. And then you can see here in the Americas, also coming from the alumina refinery. The key priorities for Hydro going forward, this is our business strategy. Sustainability is a kind of an important element in all parts. One is recycling. Recycling always makes sense from a sustainability perspective. No land use, very little emissions. We only use 5% of the energy to remelt aluminium compared to when you produce the virgin material, and also other benefits. So that's a key priority. We have increased capacity from 200 to 700 tons on recycling post-consumer scrap. We are very energy intensive, so we need to increase and sustain our own renewable production. So we have a lot of PPAs, but we also have a lot of ownership and equity power when it comes to both wind and solar and hydropower to produce our own energy. Deliver on sustainability targets, and then develop a market for low carbon aluminium. We need this to finance the next steps in our decarbonization. And this is maybe a little bit detailed graph, but in such an intelligent configuration as this should not be a problem. You all know low numbers here. Carbon accounting is complicated or can be complicated. 2018 is our baseline. That's just because we developed a new strategy in 2019. Then Hydro had emissions of 13.3 million tons. Our target is to go down to 7 million tons. That represents a reduction of 50%. But in the meantime, we have changed our portfolio. We have divested and invested in different parts, and we have basically divested, relatively speaking, high asset or high carbon assets. So that actually makes it a little bit more difficult to reach the target. But our main contribution is basically to take down emissions by 1 million ton from 2020 to 2025. So this year we are overachieving this. This is done. Almost everything comes from our alumina refinery here in Alunorte. We have replaced fuel oil with natural gas, and we have also started to replace coal boilers for steam generation with renewable. And we're also invested in 4 different wind and solar parks here in Brazil to accomplish this. Going forward, it's a little bit more challenging, but it's not a technology issue. To boil water with electricity instead of coal, it's not a technology issue. It's a cost issue. To replace natural gas with green hydrogen in the calcination, it's not a technology issue. It's a cost issue. And this is the point. There are a lot of things we can do, but costs can be prohibitive. Why are we doing this? Why are we starting why are we doing so much decarbonization here in Brazil? Well, it's because alumina is a part of the footprint for aluminium that we're selling to our customers. So as you can see, the alumina today accounts for 1.3 kilo CO2 per kilo aluminium. With the decarbonization, we will take this down to 0.4, and also some other improvements in our portfolio that will allow us to sell not 4 kilos aluminium, but 2 kilo. So, and that's a 50% reduction, but it takes a lot of investments. None of this is technology dependent. The only hard to abate element in our portfolio is the smelting process, the electrolysis. And when you look at the global aluminium industry, the average footprint is around 15 kilo CO2 per kilo aluminium. That means that it's only 10% of our emissions that are technology dependent. The rest is really more a cost element. Of course, technological developments have been very important to reduce the cost of solar and wind. But still, the hard to abate for our sector is quite small. But for us, already being very 80% renewable in our portfolio, then it becomes more important. And for us, then it is either CCS, but that's, as you mentioned, very low concentration in our off-gas. We cannot use the off-the-shelf technology that are used already. I mean, there is a lot of CCS going on now. So that's a technology issue. And then we also need to develop, we're also developing something called Hull Zero, totally new way of producing aluminium, which would be relevant only for new greenfield smelters. So I think I will leave it there. I see I've spent my time. But we can take the questions and discussions afterwards, I guess. Thank you.
Yeah, Björn, if you can already join us in the panel, we will start filling it up as we go. And it's always great to hear about overachievements during COP, right? So good news, thank you for that. And next we have Andrew Minson, Director of the Concrete and Sustainable Construction Global Cement and Concrete Association, telling us a little bit about the future of these.
Well, good evening, everyone. Thank you very much for coming to this late session. Niels, thank you very much for the invitation. So I'm representing the Global Cement and Concrete Association, and I'm sure that slide will come up in a second. So as an association, we represent the majority of producers globally outside China, and we've got some key members within China as well. Here we go. So that's a good start. That's who I am. So that's who I am, but who is GCCA? So I don't expect you to read this. I do not expect you to read it. But the first two columns are the companies who are our members, and the second two columns are the national and regional cement and concrete associations in over 35 countries and regions that are also our members. So we do not have any governance over the national associations, but we've got the same purpose and the same aim. And many of the companies that produce cement around the world are across borders. So it's the same individuals or the same companies who are on our global board as who are on the national board. And therefore, we want to work closely together. And if we don't, they tell us that we better. But it's all right, because we want to, because we've all got the same mission of decarbonising the cement and concrete sector. So what does that look like? That's what it looks like. It's easy, isn't it? You just start on the left at 2020, and you get to 2050 on the far right, and you go to zero. Straightforward. We've all seen graphs like this. So what makes this one different? What makes this one different are the CEOs in the first two columns. It's the industry who've come up with this roadmap. It's the industry who said, actually, we can deliver this technology, contribution of these technologies and the actions to get to zero. There is a but. There is a but. And the but is we need the right policy enablers in place and the right financing in place. So let's quickly look at it. It's a whole life roadmap. So it does go through all the way through to through the end of life. And I'm a structural engineer by training, originally with Arup for 10 years. So it's got a component there, which is the pale green at the top. So that's 22%. 22% is what designers like I used to be can do to use the material more efficiently to still deliver the buildings that we require, the affordable housing we require, the drinking water supply system and the sanitation, etc. All those things that make cement and concrete absolutely critical. Below that, we go through the different value chain items. We go through concrete production, that slightly darker green one. We then get into the cement and the binders, and then we get into the clinker production, which is that darker sort of red color. And then the big purple bit is the CCUS, and Niels has already made reference to the carbon capture and storage. So out of the hypothetical, the theoretical business as usual emissions, which is the top right of the graph, to get to the bottom right of the graph to get to zero, that purple is giving you about 36%. We don't think new molecules are going to help us very much. We need CCUS to deal with, Niels explained it, energy efficient. Energy is about 30% of our emissions. The reaction in the kiln, which is the limestone heating up, emitting the CO2, that bit, it's like gravity. We can't suddenly change that chemistry. So that's what we have to deal with for the CCUS. We can't just be more energy efficient. We can't just get renewable energy to deal with this. We've got this calcination process going on. So our solution to that is, well, let's have a completely different chemistry. Let's go to new molecules. That'd be brilliant. It's like the white knight coming over the hill and saving us. We've got 24 years and 8 weeks till we get to 2050. We can't wait for that molecule to come over and solve the problem. Our roadmap here forecasts that probably clinker will be replaced by maybe 5% on the new molecules. Maybe we're wrong. Maybe we're wrong. Maybe we're out by a factor of 3 or a factor of 4. Maybe it's going to be 15 or 20%. The CCUS will therefore go down from 36% to maybe 28%. It's still a lot of CCUS. We've got to get on with the CCUS now. The recognition we've had in the last 5 years, the transformation we've had, is that governments, European Commission across Europe, have recognized that actually CCUS for cement and concrete is essential. CCUS mustn't be seen as just one big technology across all sectors equally. For cement, it's absolutely essential. We have no choice. And by the way, when we're using the word essential, Niels, you said it, these industries that we've got represented tonight, we need them to society. We don't hear about the SDGs very often, do we, at the moment? I don't think. It's all about decarbonizing. 17 SDGs. Actually, I didn't know it till I looked in the detail. There are 169 actions behind those 17 SDGs. Someone nodding their head, he knows. You've probably read through them, and they're smart actions. They're measurable. I'm a structural engineer, very cautious. Building's got to stand up. It really has to stand up. I need to be very, very sure it stands up. I need to be very sure that when I look at those 169 targets and I stand up here and tell you that 81 of them can only be delivered if you've got cement and concrete, I need to be absolutely sure that I can stand by those 81, and I can. If you do that analysis, you'll get probably about 100. Cement and concrete is essential to delivering the SDGs. Niels, I apologize. I've gone so off script. Is that all right? I'll land on time. I promise I'll land on time. That was a global roadmap. Every country is different. But we're easy. We're much easier than other sectors. The same levers apply. Wherever you are in the world, the same levers apply. The weighting of them might be slightly different. The weighting of them will be slightly different, but they'll all be the same. So this is a country roadmap. So I've got a graph. So the green are the ones that have been published. The blue are in progress. The pale blue are under discussion. So good progress happening on country roadmaps. Now, they're not only important for the technology forecast of the contributions, but much more critically than that. Much more critically. It's the industry, beside government, and hopefully also beside other stakeholders, for them all to understand what this journey is going to look like, and therefore also to understand what the policy enablers are going to be. So one of the policy enablers, and I can't cover all of them, and I can't cover all the technologies, but I just do want to touch on low carbon ratings, because in all of these country roadmaps and in the global roadmap, low carbon procurement is absolutely key. We need to have meaningful demand signals to deliver low carbon products. A lot of our technologies to deliver low carbon product actually are almost at no cost. Using waste, municipal waste that cannot be recycled and cannot be reused but can be used in the kiln is a really good option for dealing with waste in society, and a lower CO2 option if your boundary is all of society. Using SCM, supplementary cementitious materials, waste from other sectors, or calcined clay, which would be a newer one, although our member in Brazil has been doing it for 50 years, so that's not that new. Tried and tested technology can mean you need less of the clinker and you get the same performance concrete. All of those things can be done at low cost, but we need procurers to be wanting low carbon concrete. So we announced in Baku with the environment minister from Germany ratings that will enable people to know what low carbon is. This builds on environmental product declarations, a completely understood, well-known methodology of communicating environmental impact within the construction sector. We don't want to undo the really great work in the construction sector in developing the EPD methodology. It's taken many decades to develop. That underpins low carbon ratings. It means that you can communicate what is good and less good in terms of carbon footprint of a product to people who aren't experts in knowing whether 100 is a good number or 130 is a good number or 250. I suspect most people in the room won't know what the number means. I don't know it when I go and buy a refrigerator and I choose to have an A or a B refrigerator, because I don't need to know the number, but I've got a rating system. That's what this does. It provides a rating system. We've developed this with UNIDO and the International Decarbonisation Initiative under the Clean Energy Ministerial. Australia just signed up to it last week. There are other countries that have signed up to it. We're delighted the progress we've made since the launch last year. In Germany, the German government has linked with the Cement Association, and they've issued their first certificates, their cement carbon class certificates, which are completely aligned with our global rating system. Australia are about to launch something in a month's time. The UK has published their implementation procedure for this in the UK, and Colombia has got a pilot running with something called the Concrete Sustainability Council. Concrete Sustainability Council specialises in responsible sourcing of cement and concrete, and they've got a CO2 module. The low carbon ratings from GCA are being embedded into that system. It's a global system, and it does everything that you can possibly do at a global level, but recognizes there are some aspects that need to be done at a local level. We've had a year. I've had a lot of conversations about it. It's not totally bulletproof. It's not totally perfect, but it's really very, very good. It's almost totally bulletproof. And we know it's fit for purpose for delivering low carbon, the definition for low carbon procurement that underpins what low carbon procurement is. Bit of background here. I stayed on that last slide a bit too long. So it's a rating system. We categorize concrete by strength. That would make sense. You could come up with a much more complicated methodology that also does by durability and by other parameters. And I suspect we will get to that. But that's very complicated to start with. So we've gone with this methodology, and the stakeholders that UNIDO convened for us, over 100 of them, which kicked and tested this, agree that this is probably a good balance between perfection and good. The clock at the back says I've got 57 minutes and 1 second left. And I don't think I do have 57 minutes and 1 second left. So I'm going to leave you with this slide, which means you can get more information on our low carbon rating system. I'll also highlight that we launched just yesterday an action and progress report, which gives an update on the action and progress from the industry collectively in 41 pages. And the next 41 pages are case studies from around the world of what our members are doing today and in the last year to decarbonize their production. Thank you very much, and I look forward to questions.
Thank you, Andrew. And such an interesting, the low carbon concrete rating is such an interesting initiative. A lot of the issues we face are about being able to cover the costs and give the right message to the market and build the market around it. So procurement alternatives are always a welcome change. Next, we have Bernhard Stormir, Vice President of Sustainability at Yara, telling us about clean ammonia as a multi-purpose solution. Welcome.
Thank you. Maybe first a very short history lesson for those of you who do not know Yara that well. We were founded in 1905, and at the time we were called Hydro. So colleague Björn is the current Hydro. We were demerged from Hydro in 2004. But the origin of our company was 1905, when we established the world's first industrial-scale nitrogen fertilizer production. And it's funny about how you mentioned that we may dream of new molecules that may save us. With fertilizers, you don't want new molecules. The basis for nitrogen fertilizer, that is ammonia, and that ends up in amino acids, which are proteins in our food. And you don't want your proteins to be something else than what they are. You want it to be exactly what it is. Worldwide, it's estimated that about half of the foods that humans eat originate from fertilizer production, and that is the result of the so-called green revolution. But I'm here to talk more about the future of ammonia, not so much about the past. We have established a special purpose company fully owned by Yara called Yara Clean Ammonia. And they are there to take advantage of the business opportunities that we find within clean ammonia. And I'll talk a little bit more about that. So there are different ways that we can decarbonize ammonia. The main process of how it's being produced, the Haber-Bosch synthesis, has undergone tremendous energy efficiency gains over the last 5-6 decades, or more actually. So we are a bit at the tail end of what can be achieved of reducing emissions by looking only at energy efficiency in the process. So what we do today is that we crack open methane molecules and we harvest the hydrogen, we combine it with nitrogen from the air, and voila, we have ammonia. And the carbon then ends up as CO2. And as a rule of thumb, in a decent ammonia plant, you will emit about 2 tons of CO2 for every ton of ammonia that's produced. If you're at the low end of efficiency, you will have multiple times those emissions, but a decent performing plant will be around there. So what may we do in order to decarbonize ammonia? So we can do carbon capture and storage. As we speak, we are building a world-scale carbon capture and storage facility in the Netherlands. The business case for that is a Dutch regulation that adds an extra CO2 cost on top of the EU ETS, which made that investment profitable. It's a triple-digit million-dollar investment, and we will have large volumes of very low carbon fertilizers and ammonia available from our plant in Sluiskil, as it's called, in the Netherlands. That will be operational in 2026. Next pathway for decarbonizing ammonia, the one in the middle, you probably can't even read it. That's doing electrolysis of water with renewable energy. And we don't necessarily need the carbon in the methane molecule. We need the hydrogen to produce ammonia. And we can get the hydrogen from electrolysis of water. And we have the first pilot plant producing what is commonly called as green ammonia based on green hydrogen in Norway. So this was and it's operational now. The first volumes are being sold to the market. It's actually, being in Brazil, it's actually quite interesting. The first 3 customers for the differentiated, very low carbon footprint fertilizers, the first was in Sweden. The next 2 were in Argentina and Brazil. So it's not so that everything green is happening in Europe. There's substantial interest also in international markets. In the Norwegian pavilion, you can get served a coffee that has been grown with a close to zero emission fertilizer. The last option to decarbonize is something we're also testing. So that is production by biomethane. And if you look towards the EU, this is comes with a certification system. So what is accepted as so-called renewable natural gas is methane coming from biogenic waste sources. So that you don't grow energy crops specifically for the purpose of producing biomethane, so you don't have competition on land for food versus energy. You use only waste sources. Here in Brazil, also a potential great opportunity using waste from bagasse, the residues after processing sugarcane. So that's also something we are looking into and considering. So I mentioned the Dutch project. We entered into an agreement with the Northern Lights, which is a carbon capture and carbon storage facility under the North Sea. This was also the first cross-border CCS agreement, which will become operational next year, as mentioned. To make this work, we needed a transfer agreement between the Netherlands and the Norwegians about how to make this a legal operation. So we will be capturing 800,000 tons per year. It will be stored 2.6 kilometers under the seabed, and it will continue for at least 15 years. And removing then 12 million tons of CO2 over that period of time. This is from the inauguration of our renewable hydrogen plant in Norway, together with our CEO and the Norwegian Prime Minister. So this is a pilot scale plant, so using Norwegian hydroelectric power to produce the hydrogen. And this operation will remove 41,000 tons of CO2 per year compared to the conventional production we have in the plant today. And we are also creating a new portfolio of products, the Yara Climate Choice fertilizers. And there will be a different range of products, so different price classes and different levels of, if you want, cleanness in terms of greenhouse gas emissions, depending on the customer needs. Looking forward, so we know that there's a growing global population. People will need more food. That said, we also see that the agricultural sector is quite inefficient in how it's using fertilizer. So we believe that the majority of growth in the future for ammonia demand is going to come from other markets than the fertilizers. And probably the most promising of them is as a shipping fuel. So long as you have control of the potential nitrous oxide emissions coming from burning ammonia, you have a very close to zero emission shipping fuel that can be used then, in particular for deep sea vessels. There's not that many other competing technologies. You can have green methanol, of course, that is one potential. The methanol, however, does lead to tailpipe CO2 emissions from the vessel, whereas that does not happen with ammonia. We foresee some smaller demand from power generation. There are locations in the world where you cannot easily establish renewable energy capacity, South Korea and Japan being two such markets. And you can also foresee that you will need to carry hydrogen from a location where you have an abundance of renewable energy to markets where there is a demand for hydrogen. So why go the route of producing ammonia first if it is hydrogen you need? It has to do with the process of preparing the gas for transportation. So with hydrogen you need minus 253 degrees. With ammonia you can liquefy it and use atmospheric pressure at minus 33 degrees. Relatively easy to handle and transport compared to ammonia, and there is an existing basic infrastructure for the global trade of ammonia today. And by the way, we are the world's largest trader of ammonia in the world. You got to put your money where your mouth is, right? So we have also commissioned the world's first ammonia-powered container ship. It will be called Yara Eide. So this will be a container vessel that will be owned by our vendor, which is doing the transportation logistics for us. It will take products from Norway and supply it to the German market based on the production in Porsgrunn, potentially then also bringing the differentiated green ammonia-based fertilizers to the German markets. And it will run on either renewable or low-carbon ammonia coming from our own upstream project portfolio. Similarly, we have started to invest into increasing our capacity for global trade of ammonia. So going to a notch up on the size of the ammonia vessels. We also see that this gives us as a company an efficiency gain in transportation. We have also demonstrated in practice how to do a ship-to-ship transfer of ammonia at anchorage so that we can demonstrate how to do this and to do it safely. So our strategy is based on retrofitting our own existing capacity, such as the project in the Netherlands. To build new capacity, we have announced that we are searching for a blue ammonia project in the US. If we find the right project, that will likely be a $4-digit million investment. When we build a new ammonia plant, which is constructed specifically to enable carbon capture and storage, we can capture 95% of the CO2 coming from production. And that's pretty good. We also look at developing partnerships and establish offtake agreements. And the offtake agreements are important. It will not be only us who are producing ammonia based on carbon capture and storage and or renewable energy. There's a project in Oman, there are projects in India, you have projects in Niger. And we have a very good position to, as the largest trader, to connect production with those markets where there is a demand. So some examples of those projects which are being executed. Slide illustrating our global position and how we are the best ones to perform these trades. Just one word at the end. Ammonia is a toxic substance, so it should not be treated lightly. I said it's relatively easy to manage, but you need to know what you're doing. So we need to have a proven design for the bunkering, for the fueling of the vessels, for how to provide that fuel to the engine. We need operational excellence. The crew needs to know what they shall do. We need standards for how to do the bunkering, storage, etc. We need the stakeholders for the whole value chain to be committed to these standards. And we need tools to support everyone who's working on this. Well, we have 100 years of experience on producing and managing ammonia. We know it can be done. And I think that's it from my side. Thank you.
Thank you, Bernard. And it's very nice to see how much of the technologies are already either out there or just around the corner. And I think I understood that you invited everyone for coffee in the Norway Pavilion sometime tomorrow. Is that it? So welcome to coffee tomorrow, everyone. And well, jokes aside, of course, the industry action is essential, but now we are going to move to the research that provides the innovation and evidence base to make the transition possible. So we will turn to our academic and scientific experts now for some insights. We will start with Espen Moe, Professor of Political Sciences at the Norwegian University of Science and Technology, talking about energy transition perspectives.
Thanks. Yeah, that's me. So I'm a political scientist, and I usually deal with the state level or the national level of analysis. I would like to say before I start that it's been extremely interesting to listen to all these great presentations on the industry level, on the meso level, which is a level that we dive into way too rarely in my line of business. So that was definitely inspirational. So energy efficiency and/or parenthesis question mark, just to make it extra weird. Energy transition, and so I'm gonna be a little bit of a contrarian, a little bit of a heretic, although I think it's basically a case of me being on a different level of analysis. So we've heard about all the great things that happen at the industry level, and now I'm going to move it one level up to the state level and tell you a little bit about how things are complicated. So first of all, energy efficiency is obviously extremely important. If you look at the IEA reports, they will tell you that 35% of all the emissions cuts by 2050 will have to be solved with energy efficiency, and in the short run even more, 50% by 2030. So these are figures that are at least as big as the figures that we expect renewable energy or decarbonization to contribute to. And obviously it's extremely important in hard to abate industries. So I think this graph is from World Economic Forum. It includes the oil sector as well, petroleum sector as well. And I think you said that in cement, only 5% of the emissions cuts will be from decarbonization, will be from renewable energy. So that tells us something about how important energy efficiency and different types of technological progress is in the hard to abate industries. But I'm also here to tell you that there is sort of a talking about energy efficiency and pursuing energy efficiency is also the politically easy solution, because you don't bump up against any vested interests. You don't bump up against any established industrial structures. And if you're lucky, you might even manufacture extra equipment that you can export to other countries and make good money off of it. So can we have both an energy transition and an energy efficiency? Yes, we obviously can, but there's also a potential trade-off here, as in renewable energy that is about structurally changing the entire energy system, is about creating an energy transition. Whereas energy efficiency approaches are basically about optimizing the existing system. It's about making the existing energy system more climate friendly. There isn't that much solid social science and sort of in the intersection between social sciences and natural sciences research on this area. But Johan Liljestam from Sweden and Anthony Patz from the US, located in Switzerland, have done a number of important studies. And what they suggest, and this is something that Johan Liljestam came up with, he said that economists will always talk about the apple tree or the fruit tree, and they will tell us that we need to start with the low-hanging fruits first because that's most cost-effective, which is typically an appeal to let's start with energy efficiency and move on once we've reformed or significantly improved energy efficiency. However, what Johan also says is that, well, we need to pick absolutely every single apple on that tree if we're going to make it to 1.5 degrees, and 2 degrees for that matter. And starting with the low-hanging ones sort of make us think that we have progressed farther than we really have. The high-hanging fruits are the hard ones, and they are the ones that typically require new technologies and years of hard research. And basically his argument and the apple tree argument is that if we focus on the low-hanging fruits for too long, well, we prioritize energy efficiency over energy transition, and so we have the trade-off between efficiency and structural change. Personally, I'm a proud Schumpeterian. Joseph Schumpeter's most famous term, which I guess most people know, is creative destruction, or waves of creative destruction. And we can easily think of the energy transition as potentially the greatest process of creative destruction, at least to the energy system, that anyone has seen in our lifetime. But some of the literature is also, including in a book that I'm writing and hoping to finish the first draft of before New Year's, a term called destructive creation. So creative destruction is all about the new entering, new technologies and new industries entering, but not being able to succeed until they've basically killed off the old industries, old energy systems, old paradigms. Destructive creation is sort of the opposite process, where you prevent structural change from happening by making the existing industries slightly more climate friendly, slightly more efficient, and slightly more competitive. If there had been someone from Equinor here, this would have been far more awkward. But some of your industries aren't equally hard hit by this as the petroleum industry. But for instance, we see record investments in renewable energy, which is a great thing. But those investments are still swamped by investments in petroleum. So finance is still supporting the old regime. Finance is still making the old regime slightly more efficient, slightly more climate friendly, slightly more competitive, and in the process postponing the energy transition instead of accelerating it. Another argument that we see from the literature is energy efficiency as preemption. So there are two main arguments in the literature as to why major carbon emitters diversify or transform themselves. The first argument is that industrial actors are able to read the future. And so if you read the future better than your competitor, you are better able to adapt to it before the competition does. So you do it in order to get a competitive advantage. Offshore wind power would be one example, especially in the Norwegian context, where Equinor for a number of years talked about offshore wind as their next new main industrial pillar. And obviously a number of things have happened to offshore wind to make it less competitive over the past few years, but you get my point. The other major argument from the literature is that major carbon emitters diversify when they feel that they need to preempt more radical measures from the state. And this is basically a greenwashing argument, where you're tinkering at the margin. It's sort of a destructive creation argument rather than a creative destruction argument. And some energy efficiency measures would easily fall underneath that heading. You could also say that energy efficiency can be thought of as a false security, especially for states that have a guilty conscience. I'm a Norwegian. We have a huge petroleum industry. The more of your climate commitments that can be fulfilled by energy efficiency, the less you need to worry about fulfilling those commitments by pursuing what is a politically costly and politically difficult energy transition. So energy efficiency measures basically increase the slack. They give you a greater margin to keep doing what you're already doing as a country. And Liljestam and Pat also make the argument that you could easily say that in some cases energy efficiency policies are crowding out or postponing decarbonization. It's especially a tempting solution for petrostates, which have an especially costly, both politically and financially, transition ahead of them, and where it's politically hard to go against existing vested interests. So to finish this off, well, 35 to 50% of emissions cuts, that's massive. That's enormously important. And in many ways, you could say that progress within energy efficiency, as well as progress within all sort of technological progress, is a side effect of a job well done. When we improve our processes, when we improve our technologies, when we invest in new equipment, well, one of the side effects is typically energy efficiency or improved energy efficiency. That's always a good thing. It's definitely somewhere we have the potential for genuine win-win. Cutting emissions and cost at the same time, and hard-to-abate industry is obviously a special case. For politicians, not just for politicians, but often the easiest way to cut emissions, both politically, technologically, and economically. But also, as a final remark, we need to maybe increase the awareness that under the heading energy efficiency, there are a number of different economic processes, technological processes, political processes. So we need to embrace the type of energy efficiency that brings us closer to an energy transition, while being aware of the fact that some types of energy efficiency measures actually postpone the energy transition and delay it. Thank you.
Please. Thank you, Espen. And nice provoking us to balance out the efficiency measures with structural energy system changes and having that on top of our heads. Next, we have Peter Nexo, who is Chief Scientist at SINTEF Energy, bringing some perspectives from technologies for emission abatement.
Thank you very much for the kind introduction. So I will be a little bit more concrete, I think, on technologies for emission abatement. I will use some past and ongoing projects in SINTEF to illustrate some of the contributions we are working on. We have made a document to this event, COP30, as a turning point, and I will use some of the advices from that report as dividers in the presentation. I will not read all these texts for sure. So, but energy efficiency, I believe this is very important in addition to all the other tools we need, because you need to harvest all the apples, as you also indicated. And then in energy efficiency, it's extremely important, and also for the equipment for more personal air conditioning and so on. It's very important also from the grid point of view. I'll come back to that. So one project we have been focusing on, we had a research center called HIEF, focusing on energy efficiency in the industry. And there we focused on, of course, doing the core process more efficient, but also to utilize the surplus heat to capture this at the highest possible temperature in order to use it directly for district heating, for instance, or whatever, or by elevating the temperature of the surplus heat using high temperature heat pumps and so on. In combination with the energy storage, this is enabling technologies to improve the energy efficiency by utilizing this heat internally in the industry, or this energy in energy clusters using surplus from one industry into a resource in the other industries. So quite important. You said that energy efficiency could be not or delaying the process. But when we see power supply and the energy system, it's big challenges in both building out new power grids, but also to utilize the ones better that we already have. So a growing portfolio at the moment is industrial flexibility projects. And I will use one of these. These are 4 projects that we are involved in, EU projects. One of these projects, Flex for Fact, is an EU project where we demonstrate the possibility to introduce renewable energies and hydrogen and so on into industrial processes in different industries around in Europe. Another example is from a recent PhD study that was published just months ago, utilizing industry areas as a flexible element in the grid, and then reducing the peak demand by maybe 15% potentially in a market. And but this of course requires much more coordination between the industries, and the industries being willing to open the flexibility they could have in their system. But it could actually also drive an economical benefit for the industries, was the results from this work. The third area I will talk about is hydrogen, and hydrogen then also covering hydrogen derivatives like ammonia, of course. So we have a big research center called Hydrogen, where both hydrogen and ammonia from production to storage and transport to end use is focused, and also very much on the safety aspect, so ammonia and hydrogen and so on. So, but I will use another example. We have a project called H2 Glass. This is focusing on how to utilize hydrogen in the glass industry in order to decarbonize the industry. It's then focusing on different elements of this chain, like the combustion and so on, demonstrating green or decarbonized glass. This also has a spin-off to hydro, actually, on Hydro Havran. I don't know what is the status on that at the moment. We believe that carbon capture and storage is a large or important technology in order to try to reach the 1.5 goal. It's difficult to see how we can do without it, and especially important maybe for hard to abate industries, like we have heard from cement and so on. And now we are running an EU project called Core EU to look at a transnational infrastructure and logistics network for carbon capture and storage, linking different CO2 emitters with storage and transport, and focusing on different elements in this. So collaboration with the Global South will obviously be very important also in this, in order to contribute to emission reductions also to the Global South. We have some projects with Africa, India, and other parts of the of the world, but we would like to grow this project portfolio much more. And we have some applications ongoing that we hope will go through. So these are the 18 chapters we have in this report. And you also have the link to download this report at the bottom here. Thank you very much.
Thank you. Thank you, Peter. And for those interested in the report, I think all the copies we had at the Norway Pavilion are gone now. But as Peter said, we have the link here, but if you look it up, COP30 NTNU SINTEF, you can find it online and it should be quite easy. Otherwise, get my business card at the end of this session and I'll make sure to send you the link. So our last panelist today is Michiel Schaffer. He is the Chief Scientist at Climate Analytics, with now an economic perspective, an economic analysis of the steel sector in Japan and the fertilizer sector in India. Thank you.
Thank you so much. Well, it's a pleasure to be here. I was very excited by the presentations by the panelists from the industry sector. There are a lot of things that we would like to follow up on, so I hope you will stick around for a few more minutes after the event. Here are the slides up, please. So my name is Michiel Schaffer. I'm Chief Scientist at Climate Analytics and a Professor of Climate Science at the International Islamic University of Indonesia. Climate Analytics is a think tank on climate science and policy, where we provide, in particular, already for almost 20 years, scientific and technical advice to what we call vulnerable countries, climate vulnerable countries across the world. We work a lot with small island states, with least developed countries, and it's also from that perspective that I will approach some of the questions that we have on the table today. For the climate negotiations right here, and for the countries that we work with, 1.5 degrees remains a central topic, and it is a topic of survival. And so over the past few years, we have started 3 research tracks that I would like to bring together here. One is 1.5 degrees, we're almost there. It's 3-5 years until we reach long-term warming of 1.5 degrees. And so what happens then? Can we still get back to 1.5 degrees? If so, after how large an overshoot and how long an overshoot? So that's one piece of research. Secondly, based on the global energy system modeling that we do to answer that question, what does it mean to sort out the reality on the ground? And that's one reason I'm excited about the first 3 presentations tonight. And we have been looking at some difficult sectors. And the example I want to focus on is the fertilizer sector in India, because that nicely connects to the presentation by Yara tonight. And I'm ending then with a final research track. We also are partners here for you to speak with, Moya Analytics in Singapore. That looks even broader system perspective of international connection of energy systems between countries, such as the trade of green ammonia, green hydrogen, and also cross-border grids. So first, the IPCC scenarios that inform the negotiations here, that inform national policies on 1.5 degrees, are a couple of years old and in some sense outdated. Current present-day emissions are not at the level that they should be in these scenarios. As we can see here, they started reducing already in 2020. And also the progress in certain technologies, not all technologies, has been faster than many of these scenarios include. So our new scenario that we just published 1.5 weeks ago, you see here in the blue line compared to the IPCC scenarios in the green colored range. is slower to reduce in initial years, then picks up pace and surpasses the IPCC ranges to get to below zero emissions ultimately in the latter half of the century. So what does it mean for warming? It means that we will exceed 1.5 degrees substantially to 1.7 degrees roughly, and then reduce warming to then again reach roughly the IPCC levels towards the end of the century, which is about 1.2 degrees, so well below 1.5 degrees. This is a huge challenge, such as 1.5 degrees always was a huge challenge, but we will show that it is as economically feasible as we thought 1.5 degree was, if there had been the political will to stay below 1.5 degrees. One key ingredient here is CCS, but maybe not in the way that you may expect. I agree with the number of the speakers before that CCS is needed for some sectors, but it needs to be very, very limited for a reason that most people may not realize, which is, let's say, our speaker, chief scientist of SINTEF, mentioned cross-border CCS. We also need to think about cross-generation CCS. We need CCS at a large scale in the latter half of the century in carbon dioxide removal technologies, direct air capture and CCS, perhaps biomass and CCS. These technologies are essential to be able to bend the curve and to come back from 1.7 back down to 1.5 degrees. That also means that given limitations in global capacity of CCS storage, we need to make sure that we limit it to the CDR technologies that we need and to only the very most necessary use in other sectors such as industry. So process emissions are a good example. So in relation to this, we have been working with Fortescue, you may know, a large mining company based out of Australia, to work on the concept of what they call real zero. And real zero is the idea that we limit CCS to the absolute necessary elements in a process cycle and nowhere else. And this can be done in different sectors, and the idea is that in many sectors there are already technologies that exist and need to be scaled up, need to be supported by policy, as previous speakers identified as well. So we have been looking at one particular sector, the fertilizer sector in India, and just to give you a bit of perspective, the speaker from Yara already mentioned Brazil, Norway. We've been looking at India. It has a large fertilizer industry, and it is one of the largest consumers of fertilizers in the world. And that also makes it economically vulnerable to, for example, volatility of LNG. Much of this is gas-powered, and prices of fertilizer in India are very tightly connected to energy prices, which makes it a budgetary problem for the government. Now, there's been a lot of progress, obviously, in the prices of renewables. I won't get into much detail. India has, interestingly, a strategy of not pushing on CCS in the fertilizer industry, but push on green ammonia production pathways. If you looked at the slides from Yara just now, there were 3 pathways of decarbonization. The middle one is more where you find this green ammonia pathway that we've been looking at. So we looked at one particular question, which is by when, given renewable energy capacity and potential in different states in India, by when would in each of these states green ammonia decarbonization pathway become competitive with gray ammonia? So the levelized cost of ammonia, when will they cross with gray ammonia? And this already happens in some states in a few years from now, with slight improvements only in the the levelized cost of renewable energy, and not long after in many other states across India. So we see a clear competitive advantage emerging in India in the next 10 years, which is one reason why India does not bet on CCS in this particular sector. And it's also expressed in recent auctions across India. We have one example here with a recent auction where the winning bid is actually at cost parity with gray ammonia. Now, briefly on steel in Japan, very, very hard sector. We all know this. That's why we wanted to look at it. Japan produces, I think, 14%. Emissions are 40% of Japan's national emissions. And there's a lot of strategy related to CCS in this area. We've looked at several options. We cannot find a solution where we have a full real zero pathway that is competitive. So that would need substantial policy support, if not carbon pricing, except when we include certain import trajectories of green iron ore. Then finally, because I realize the time is limited and we need at least some time for discussion, this third research track, and this introduces, I think, a completely new perspective that in all of the scenario work in IPCC and in our institute is not included, which is what happens if you connect grids of countries or when you start trading green energy carriers instead of fossil fuel carriers, which we are used to do. So our Global Mitigation Potential Atlas is a relatively new project paid for by the Singapore government in collaboration with the Dutch government, where you can, I will show you the link later, the user can look at different countries, see interventions required, technology required nationally to go to zero emissions, but then in a very flexible way be able to couple that country to any other country and see how if you couple these energy systems, the overall system becomes much more efficient, right? Because balancing of renewables is simply more efficient if you include larger geospatial areas and different seasonal cycle zones, etc. Costs overall reduce dramatically to get to zero emissions. Some cases 20%, some cases 30%. In some cases, such as this example, the ultimate cost to get to zero emissions of South Korea, Malaysia, Indonesia, and Philippines together would actually go below a business as usual scenario. So at net benefit to the economies of these countries. So with that, I want to finish my presentation. Thank you very much.
Thank you very much. So let me just, I'll leave the QR codes there for a few seconds in case anyone wants to take a picture, so you have time for that picture while I introduce. I do have a lot of questions, but I will open for the audience as well, because I think I'm a bit greedy if I don't do that. And I wanted to start, I had a lot of questions planned, but I think one of the things that struck me the most is the challenges in market for such solutions that we are discussing. And procurement alternatives were brought up, but I was hoping if any of you who feel that you have a say in it could mention a little bit of what policy, what regulation, what alternative procurement methods, what do we lack to make these even more relevant and more fast-paced than we have now, such technologies that were discussed today. Any candidates?
I'm really interested. I love your questions, but these people have come here late. I want to hear their questions as well. So low carbon procurement, we just want public authorities to specify low carbon procurement as well as cost and time and quality. When you build your new house or extension, you traditionally go cost, time, quality. We need to put carbon in the middle of that. Therefore, we need low carbon procurement to be fundamental.
I mean, are there any questions in the audience? You know, it'd be really good. Yeah, fine.
Yeah, thank you very much for very interesting presentation. So I'm just wondering, like from my understanding, for hard to abate sectors, like carbon capture and storage has a lot of potential, and a lot of reduction should be based on carbon capture and storage. But for example, for developing countries, carbon capture and storage is still very expensive. Yeah, and we had a consultation with cement industry, for example, in our country, and they're saying that it's still very expensive. And there are a lot of competition, international competition for cement, and it's very hard to like implement carbon capture and storage. And my question is, could we expect any any price reduction and like to make it more like feasible, economical feasible? Could we expect any technological improvement to reduce the cost of carbon capture and storage? Thank you.
We're not expecting, unfortunately, the bad news is we're not expecting economies of scale that we might have seen in something like offshore wind, and nowhere near what we're seeing in solar to apply to carbon capture. But I'm really hoping people on my left, all right, are going to say, yes, we know how it's going to be cheaper.
Well, I mean, it has become cheaper than it was like 20 years ago. I think what was alluded to here as well, when you get large-scale infrastructures which can take care of the CO2, so you can deliver somewhere and you can get it stored, you know, rather than having one storage site connected to one emissions source, that will help a lot. But I also think, as we saw from the roadmap for the cement industry, that you need to go through these steps, you know, what other items you can do as well. But there is no doubt that you would need this to decarbonize cement, which I'm pretty sure you know all about, you know, to go towards zero. And even if you account this uptake also in the concrete over time and so forth. So I don't really see how we can change this a lot in terms of the solution, although there are activities on using clays and other materials as well. But then there is the strength of material, of course.
Thank you all, the panelists, for the nice presentations. I have one question for the industry leaders. I think the scope of the presentation is saying that it's okay to have solutions and technologies for the hard-to-abate sectors. However, the issue is usually the cost. So the question now is, who will bear such costs? Will it be the consumer in the end? We will have to, in order to finance such a transition cost for the decarbonization, will the consumer be the one paying, or maybe the countries, or whom? Especially outside of the EU, maybe the EU, we have the emission trading system, which is now, you know, have a cap, and it's not easy for the industrial factories to go lower. So let's ask about another countries who will be financing such cost of technologies. Thank you.
Maybe I can go first on that one. So considering ammonia fertilizers and the food markets, I agree that green ammonia, so based on renewable energy, will be cost competitive. I might not be as optimistic on the time horizon as you are, but let's discuss afterwards. On the current energy prices and technology, the fertilizer will be significantly more expensive than today. If there was a regulation that would dilute that cost to the end consumer, for a loaf of bread, that would be like a handful of euro cents added to the costs. So already today, yes, the food would become more expensive, but that cost is not prohibitive. However, we don't believe it's realistic to put such a regulation in place. In some years, it will be cost competitive, and then the industry will transform as new investments are coming.
Yeah, I think it's a very good question, and I think it's one of the big questions that we don't spend enough time on discussing. But I think it depends on how you design the system. Right now in the EU ETS, basically quotas are created out of thin air by the governments and then handed out or sold out. So handed out to industry that are subject to carbon leakage and sold out to, for instance, the power sector. With the introduction of CBAM, this changes. Then the cost will be borne by the consumers in Europe, because prices in Europe will go up to cover the cost of the loss of the free allowances. So in that sense, it's a transfer of wealth from the consumers to the governments. So I think, and this is how should this be done? I think someone will have to pay this either through the price as a consumer, you see it straight away on prices, or ultimately consumers that are taxpayers will have to pay it if you do it the other way. I think it's not realistic to think that the industry or the shareholders of industry will take the whole cost. That's not how the capitalist system works.
I'm sorry to interrupt, but we ran out of time and we are required to wrap up our session. So I apologize. I know there's a lot of great questions still in the audience and a lot of great comments from our panelists, but we do have to wrap up. So I just want to thank all of our panelists for the insights, our audience for joining us at 8 p.m. in Belém today. It is amazing to have so many people here with us. So thank you very much to everyone, and hopefully we will all have a great COP ahead of us.